Hi everybody, I'm Elisa Bortolas from the University of Milano Bicocca, and today I'm going to tell you about the spiral of massive black holes. In particular, we know when two galaxies merge, and if they both host a massive black hole in their center, then the two objects may spiral towards the center and shrink from the kiloparsec scale at which the galaxy merger happens down to the milliparsec scale at which gravitational waves may be efficient in ensuring the massive black hole's coalescence. And those gravitational waves may be detected by forthcoming facilities like Elisa or the pulsar timing array. So we do really want to model properly the spiral and the different phases of it in order to have a realistic timescales associated to them to obtain realistic rates for those observatories. And in particular, today I'm going to focus on dynamical friction, which is a sort of gravitational drag against dark matter, stars, and gas that models the large scale in spiral. And I'm going to try to convince you that this may not be the full story. In fact, what you see here is a snapshot of a zoom-in cosmological simulation from redshift 7 to roughly 6 of this typical main sequence galaxy. And what I did is to put several massive black holes in the galaxy, and those black holes, they all share the initial orbit when they evolve in this realistic galaxy, but just they are put in a simulation with a different orbital phase. And what I found, and here you see 3 examples, is that the massive black holes may take a very different time to reach the center, even if their initial orbit was the same. In particular here, 2 out of 3 reach the inner 100 parsecs, which is the resolution limit in roughly 150 million years, but one of them gets ejected from the center and even doubles its initial angular momentum in the same time. So we asked ourselves, why this? And in order to better investigate it, we decided to compute the global torques that each massive black hole suffers as a result of all the mass distribution inside the simulation and compare it to the dynamical friction-induced torque, where dynamical friction torque and force is computed by these traditional semi-analytical formulas. And what we strikingly found is that the dynamical friction is typically a factor of 10 or less efficient than the large-scale gravitational torques acting on each massive black hole. And this is particularly true when we see a bar forming in our system. In fact, you see here the global torques all shoot up and the evolution get really, really driven by it. And so the message here is that dynamical friction may be less relevant than the global large-scale torques in determining the spiral and the time scale for it, which then can turn to be very stochastic. And in order to better investigate it, here I'm going to show you some preliminary results in which basically we took a Milky Way-like galaxy with a dark matter halo, disk, and the bulge. And in this Milky Way-like galaxy, we also put we also added a barred case in which part of the disk and bulge mass was converted in a triaxial structure here. And we basically evolved a large number of orbital integrations in this potential that also takes into account dynamical friction effect. And we compared the case with the bar and the case without the bar. And here, what I'm showing in this preliminary result is the time scale for the spiral as a function of the orbital phase, initial orbital phase. In fact, those are all coplanar prograde in spirals in the beginning. And what you see here is that when the bar is not present, the time scale from the spiral is this line here, for instance, but in the same at the same time, when the bar is put in the simulation, then the time scale can vary depending on the initial orbital phase with respect to the bar, and in some cases can get to half the case without the bar, and sometimes the inspiral may be hindered for more than a Hubble time. Here is a similar situation in which the initial orbit was a bit different, and in this situation, the non-barred case would not ensure the inspiral in a Hubble time, but if the bar is put in, then we have a lot of situations in which the inspiral is ensured. So this is just to tell you that the evolution of massive binaries in a realistic galaxy environment may be way less predictable and very stochastic. And in particular, the global large-scale torques, especially if there is a bar in there, may be more efficient than dynamical friction in determining the massive black hole in spiral time scale. And this has to be tracked down more in detail in order to make predictions for the future observatories. And also, even in a pretty typical Milky Way-like galaxy, like the Milky Way with its bar, then we find that the bar can significantly impact the spiral time of the massive black hole, sometimes reducing it even by a factor of 2. So thank you very much for listening. And please feel free to send me any question you have. Bye.